EE World. I'm Senior Technical Editor Martin Rowe. We are in Brooklyn, New York at the Brooklyn 6G Summit. This is the NYU Tandon School of Engineering. And Yahya Shabara is going to give us a demonstration about integrated communications and sensing as a possible technology for 6G. And he is with MediaTek, and MediaTek has been working with Keysight on this. So why don't you tell us what we're seeing here?
Sure. So this is a TDM radar joint communication sensing demo with Keysight. We're trying to display or demonstrate that sensing performance can be achieved with a sparse signal, so it wouldn't have large overhead. And we're achieving like only 7.5% capacity loss as a result of the integration of radar or sensing into the communication link. Okay, so this is an implementation of an existing 5G ISAC. This implementation is done in China, where half a slot is blanked out for sensing function. And what they do is they send a sensing waveform, so this is different from the OFDM. They do pulse radar in part of it, and then the other part will be continuous wave. The problem with this is that they end up having to block an entire time slot for this, because even blanking half a slot is an optional UV capability, so maybe not all UV support that, then they're stuck with blanking out the entire slot. This is a large overhead that we hope to improve. So what we propose instead is, instead of slot level blanking, we can do OFDM symbol level blanking, and we can try to make this signal or this sparse OFDM symbol reserve symbols for sensing non-uniform and sparse. The exact design would be to try to minimize the ambiguity in the Doppler spectrum. We try to solve an optimization problem, basically, where we can choose the number of sensing occasions and the exact timing of those. To achieve this demo, we try to use dynamic rate matching. It's an optional and advanced 5G capability. So what we have here is a UE test phone. It's just similar to this one, and we hook this up to a GNRB 5G UXM whole box from Keysight, and we declare that we're capable of rate matching here, and the network side, once it does this RRC setup, sends the exact bit map where marking the locations of the OFDM symbols we want to reserve for sensing, and this can then be dynamically indicated using DCI. So switching between like an ISAC mode where you reserve resources for sensing versus like a communication mode can be very quick and dynamic.
So this is one possibility for ISAC that might make its way into 6G.
Correct.
Okay.
Yeah. So what we're trying to show here is that the sparse signal design, that we're saying that this does not have to have a large overhead, and we still have good and reliable sensing performance. And if this is a native feature in 6G, unlike what we're trying to do here, achieving with some advanced 5G features that's likely not going to be available in all UVs. If it's a day one 6G technology, or at least it's planned for day two 6G technology, then this will be achievable with low overhead. Okay. So this is the setup of our demo. We have like the Keysight 5G call box here. It's hooked up to our UE. We're doing a conductive test where we have a 4x4 MIMO link, and in the background there's two monitors, the one here showing the throughput. And if you focus here, there's like a dip in throughput. This is where ISAC is happening, and the high throughput would be the communication only mode. So you see there's a slight dip. This slight dip constitutes like 7.5% loss. So we showed that this is just a sparsity in time, and we're achieving 7.5 loss. And if we do also sparse design in the frequency domain, then we can achieve even lower overhead or lower capacity loss. And maybe one more thing to show you is a video demo. So we have a toy train to achieve this. And because we have a toy train on a very small scale, the 100 megahertz bandwidth of the 5G link is not enough to get us enough range resolution. So we end up using a millimeter wave radar chip. This is like a previous MediaTek product, but the intention for 6G is for this to be in-band actually.
So you're using millimeter wave for this?
Correct, yes.
Okay, what frequency?
This is a 77 gigahertz.
Okay, 77 gigahertz.
Right, and the bandwidth is 4 gigahertz. This gives us approximately just below 4 centimeter resolution.
Okay.
And this is good enough for for a tabletop toy train to run and then see actual movement.
Okay.
But with the 100 megahertz of the 5G link, it gives us 1.5 meters of resolution, which is not enough to see any movement. So just for demo purposes, we do that, and also for licensing issues. Like this millimeter wave spectrum, the one that we use is unlicensed, so
Right.
also saves us this trouble.
Okay, very good. Thank you.
Yeah, thank you so much.